Welcome back. In this video, we're going to continue Chapter 7, and now we're going to look at concepts of heat and work in thermodynamics. And our goal here is to understand the mechanism of how energy is transferred between a system and its surroundings. Now, consider a collection of atoms or molecules. We know from the previous chapters, particularly the chapter on electrostatic interactions, so we know that there are attractive and repulsive forces acting between these atoms or molecules, and those forces are keeping them together and occupying some finite volume in space. Now, how do we transfer energy in and out of this collection of atoms or molecules? Well, we know from Chapter 1 that an external force that's acting on this collection will cause displacements, and those displacements integrated with the force, the dot product of the force times the displacement vector, integrated over the path, will give us the work that we do on the particle. And we also learn from the work energy theorem that the work done by the force is equal to the change in the particle's kinetic energy. So for this collection of atoms or molecules, we could calculate the energy transfer by just looking at the sum of the kinetic energy differences. So the difference before and after is going to give us the total energy transfer. The problem is that for 10 to the 23rd atoms or molecules, we have no hope of tracking all those individual velocities before and after the force acts on the system. So it's not going to be something that we could do in any practical way on a real thermodynamic system. However, we can in thermodynamics still track this energy, but we do this by dividing it up into two different contributions. And one of these contributions we're going to call thermodynamic work, which is effectively work like we learned it in the first chapter. And that's the work that's done on or by the system that leads to displacements in the system's macroscopic coordinates. So the observable coordinates that you can see on a macroscopic scale, the center of mass of the system, the volume that it occupies, or maybe the surface area that it has, all of those macroscopic quantities we can observe, and we can see their displacements, and we can calculate, just like we did using the equations of Chapter 1, the work that was done in those displacements. On the other hand, there's going to be work that's done that doesn't lead to any macroscopic observable displacement. So there'll be changes here in the kinetic energy due to work, external forces acting on the system, and that will lead to displacements of the microscopic coordinates, but no changes in the system's macroscopic coordinates. So for those, we can also measure those, but we're going to measure those through the heat flow that's going in and out of the system. All right, and we'll see more about this here shortly. So let's just look first at thermodynamic work, just make sure that this is clear. So when I have a collection of particles and I have an external force that's acting on them, I know that if this force displaces the center of mass along some path, then I can just simply do that integral along the path and use the displacement of the system's center of mass to calculate the thermodynamic work. Okay, so the work in this case, because it's a work involving a macroscopic observable quantity, I'm calling it thermodynamic work, but it's calculated just the same way as we would have calculated in Chapter 1. Similarly, if I take the collection of particles and I apply some uniform external torque to the system, I can cause the system to rotate. So there's a torque causing a displacement, change in the orientation of the system, and there's a work associated with that displacement, and we can calculate that, and that will be another example of thermodynamic work, a work that we can calculate based on a macroscopic displacement of the system, in this case, its orientation. Similarly, we could apply radially directed forces onto our system of particles that would cause the particles to be pushed into a smaller volume, and that the work of these forces would lead to an observable displacement in the system volume, and that change in the volume then we can calculate from the external forces and the volume change, we can calculate the work that's associated with that process. So this is another example of what I call a type of thermodynamic work that leads to a macroscopic displacement. But again, it's the same principles, the same equations that we would have used in Chapter 1, but we're using it for the macroscopically observable displacements and generalized forces that are causing that. Now, when it comes to the displacements that don't lead to any type of macroscopic observable coordinates. So if there are external forces that are acting on our system of particles, but there's no observable macroscopic coordinate displacement, well, there still can be energy transfer, changes in kinetic energy. We just can't observe any macroscopic coordinate displacing, but what we do see is that there is a change in the temperature of the system. And that change in the temperature is a reflection of that increase or decrease in the kinetic energy of the system particles. And that mechanism where the forces cause microscopic displacements but no observable macroscopic displacement, that mechanism is what we call heat. Okay? So whenever we heat an object, what we're doing is the heat that's transferring across this boundary is essentially applying forces to the molecules inside our system, but they're not leading to any macroscopic displacement, but they are increasing the kinetic energy. And because the kinetic energy is increasing, we know that kinetic energy is related to temperature. We see an increase in the temperature. So we can then measure the heat that flows by just looking at the temperature change and determining what the proportionality constant is between the heat flow and the temperature rise. So this proportionality constant is what's called the heat capacity of a system. And I'm sure you remember these from your undergraduate freshman chemistry course, all of the heat capacities values for all kinds of different substances. And those are the proportionality. It tells us how to relate the temperature change to the heat that caused that temperature change. And again, this is the differential equation, but that's generally speaking a path integral. You have to integrate it along the path. This heat capacity could in generally be temperature dependent, so this is not going to be pulled out of the integral and done so easily. But sometimes it can. As we saw in the chapter on kinetic theory of gases, sometimes the heat capacity for gases and ideal gases will be independent of temperature. Okay, so now let's turn back to the thermodynamic work and focus on that contribution. We learned that that's a displacement along some macroscopic coordinates. So a classic example of that is the differential work of gas expanding in some piston cylinder apparatus, which we've seen in the previous lecture. So you imagine you have some pressure that's acting on some piston head, which has some area A. So the pressure is just a force per unit area. So if I take my definition of work here, which work is minus F dx, and I replace F with P times A, that's the force that's on the face of the piston, the area of the piston, and then I recognize that A times the displacement is just the change in the volume, then I get this equation for the differential work associated with the change in the volume. So what we have now is a displacement, which is the volume, and a generalized force, which is the negative pressure that's causing this minus P, which is negative pressure that's causing this displacement here. Okay, so that's just one example, but there are other types of macroscopic coordinates, as I showed in the previous slides. So generally what we can do is we can look at all of those macroscopic displacements. So I'm going to write a more general equation where I do a sum over all the possible ways in which we can observe thermodynamic work, displacements, generalized forces that cause displacement in macroscopic coordinates. And we can write them in this general form here, and we sum over 1 to beta. Beta is the number of generalized works that we have. And so we write these down, and y is our generalized force, and z is our generalized displacement. And usually this is going to be some kind of extensive property. So in this case, for example, it was volume. And this y, the generalized force, will be an intensive property. And in this case here, it was p. But if I go to a table of these, here are all the generalized forces that we will encounter. And here are all the generalized displacements. So we see, obviously, the one pressure and volume. Gives us this work, differential work, which is minus PdV, and that's one that we'll use over and over in this chapter. There are other types of macroscopic displacements, and so, for example, there's the elastic deformation here, so there's a force, and then there's the displacement in length, so FdL is that one, that differential work, or changes in the surface area, so you have change in the surface area of the material, and this generalized force is the surface tension of the material, so that becomes the differential form for the work that's done through this macroscopic displacement. We can also have matter being transferred in and out of the system, and that's an energy transfer too, because there's energy associated with matter, and that is given by this differential form. So the generalized displacement is the amount, the number of moles that you're moving in and out, and then this term is the energy associated with those moles that you move in. This is what's called the chemical potential, and the differential work is mu dn. And we can also have work associated with fields. So we can have, for example, a change in the charge of the system, and there'll be the potential energy, the electrostatic potential that is moving this charge. So we can have Q, phi times dq, which is our differential work associated with the potential, electrostatic potential that's moving charge across the boundary. We can have polarization. So if we apply an electric field and we polarize the sample, then there'll be work associated with polarizing the sample, which is E dot dp. This is not pressure. This is polarization, electric polarization. Similarly, we have magnetization. So if we put the sample in a magnetic field, that's our generalized force, and the magnetization is the macroscopic displacement. So B dot dm is the differential work associated with magnetizing a sample. We can also have a gravitational field and displacing the system along some height. That will be a differential work of mg naught dh there. So you can see that there are multiple ways in which we can put energy in and out of the system through a macroscopic displacement, which is work, as we learned in the first chapter, but now because it's associated with macroscopic displacement, I'm calling it thermodynamic work. All right. Okay, so that's it for this lecture. In the next lecture, we're going to look at work in reversible and irreversible processes.